Okay, so we're going to pick up here where we sort of left off. We got into obviously chapter 1. We talked a little bit about scientific method, but mainly we talked about the atom and a number of sort of important experiments that led us to a better understanding of the atom. Really, it all started sort of with Thomson, who again used those CRT tubes to figure out the charge to mass of an electron, followed by sort of Milligan, who did that oil drop experiment, was able to figure out the charge of an electron. And again, from both of those sort of important experiments, really the mass of an electron was determined. And again, it was something like 9.09 times 10 to the minus 28 grams, very small mass. Sort of further understanding after that point, as we talked about, was the idea that the atom was sort of neutral. Obviously, electrons being negatively charged. That came up with Thomson coming up with the plum pudding model of the atom. And again, that was that sort of spherical model where all the positive charge was sort of spread out over it. Embedded inside were these electrons. And it was thought of at that time that most of the mass of the atom was made up of those electrons that were embedded inside. And this was sort of the model that was sort of put forward until really the next big sort of thing that occurred, and that was Rutherford, who did the gold foil experiment. And again, they anticipated that the alpha particles that they shot at the pieces of gold foil would sort of go through, like we talked about, with some deflection as you're shooting sort of positive at positive. And what they found was sort of the opposite. Again, most of them went through undeflected. Every so often, things were sort of bounced off at large angles. So they had to really revisit this model of the atom and sort of say, not so correct here, and come up with sort of really the modern version of the atom, where we have in the center a very dense positive core, which is our nucleus. Most of the atom is empty space, and that is where we find our electrons sort of randomly moving about the nucleus. And most of the mass of the atom is actually made up of the nucleus, which has protons in it and neutrons. And as we saw through later experiments, neutrons being the sort of heaviest of all three of those particles, protons, electrons, and neutrons, and protons very, very close in mass to a neutron. So each of those guys, a proton and neutron, is about 1,800 times heavier than an electron. So again, that makes sense that the nucleus where they are found is most of the mass of the atom. Once again, electrons moving pretty randomly about the nucleus. There is some attraction, obviously, as we talked about, between the electrons and the nucleus as they are oppositely charged. So there is definitely an attraction. And as we talked a little bit about last time, and we'll see in later chapters, again, that is the reason why only certain electrons are involved in things like bonding and other ones aren't, because they're very close to the nucleus and held very tightly. We then sort of moved on to talking about isotopes, which are really the same element but have different masses. And really the difference is they are same protons but different neutrons. And obviously that is why they have obviously a different mass. Thank you. Part of that as well, that we could look at some important things of an atom. One is the atomic number. The atomic number is the number of protons in an atom. That again is found on the periodic table. That is our number that we see above the symbol is the atomic number. We also have the mass number, which is our number of protons plus our number of neutrons. That again is not found on the periodic table. Again, the number on the bottom there is not the mass number. When you do calculate, as we talked about, protons, electrons, neutrons, mass number, atomic number, they do need to be positive whole numbers. And again, if you look at the periodic table, Pretty much all those numbers underneath the element symbol are pretty much decimals type numbers, so they're not whole numbers. But the importance of these two numbers is, again, you could take the mass number and subtract it from the atomic number, and that would give you your number of neutrons that there are in a particular atom. We can write these guys in sort of symbol form, where we use the symbol, and up on top left is the mass number. On the bottom left there is our atomic number. And again, just basically subtract the top number from the bottom number. Another way, again, as we saw, sometimes these isotopes are written is like the symbol and then a number. And again, that number is the mass number when it's written like that. Like I think we did copper 64 or something like that. So when we see that number written like that, again, is the mass number. You can get the atomic number from the periodic table. As we talked about, it is the protons or the atomic number that determines really what element you're talking about. No, every element has its own atomic number and number of protons, obviously, which is the same definition there. So if you know the protons, you know the atomic number, which is basically the same thing. You could just simply go to the periodic table and figure out what element you're talking about by finding the correct number. Everybody has protons, electrons, and neutrons except for hydrogen. Hydrogen has just a proton and electron, does not have a neutron along the way. Any questions on any of that stuff we talked about last time? Okay. So I think we finished up an example last time. So why don't we try these examples here? Write the symbol that includes the mass number and atomic number for each of these guys. We got krypton with 48 neutrons, nitrogen with 6, and iron has a mass number of 56. How many protons, electrons, and neutrons? So take a couple minutes, see what you come up with. Let's take a look, see how you're doing. So again, in this case, we have krypton, which has 48 neutrons. So we would want to go to the periodic table. If we go to the periodic table, we find krypton there at number 36. Again, that top number is going to be our atomic number. It's also going to be obviously the number of protons that we have. So we would start with Kr. Atomic number should go bottom left there. And obviously our mass number going to be our protons, which would be 36, plus our neutrons, which would be 48. And that's going to give us 84, I think, 84. That would go up here on the very top there. Any questions on that one there? Looking at the second one is nitrogen. So again, you don't really have the atomic number, so you could go to the periodic table. You look at nitrogen, it is number 7 on the periodic table. So once again, that would be our atomic number, which would go on the bottom left. It also obviously means that nitrogen here has 7 protons. It also would have 7 electrons since it's neutral. To find, again, our mass number, we're just going to add both of those numbers together. That is 7 protons plus 6 neutrons, gives us 13, which once again would be our top number up there. For the last one here, we have iron, which is Fe, is iron. And again, if we go to the periodic table, Fe is 26 up on top. So that would definitely be our atomic number on the bottom left. In this particular case, they gave us the mass number, which would be 56 up there. At this point, it also wants to know protons, electrons, and neutrons. So there is no charge. We're assuming it's neutral. So the number of protons here would be 26. That would also equal our number of electrons, as they have to cancel each other out in terms of the charge. And our number of neutrons in this case would be our mass number minus our atomic number, which would give us 30. Any questions on any of that there? Questions on how to calculate protons, electrons, neutrons, mass number, atomic number? All right, so before we move on from this, we've talked about here in these last couple of examples, things that are obviously neutral, but let's talk a little bit about what would happen, obviously, if we had something that had charges. So if we did come across something with charges, and things that have charges, these are what are referred to as ions. And there's really kind of 2 types of ions. There are what are referred to as cations. And those are positively charged ions, things that have positive charges. There's also negatively charged guys, which are referred to as anions. So we'll take something like, I think we had nitrogen there, 13. And obviously with no charge, as we just kind of looked at, the number of protons there would be 7. The number of electrons there would be 7 as well. Again, positive and negative gives us no charge overall, which is what we see. And obviously our neutrons is still going to be the 6 there. 13 minus 7 gives us 6. Now, what if we took the same guy, but it did have a charge, say something like a -3 in this case, which is typically what nitrogen can make. So if we have something with a charge, we do have to adjust certain things. Now, when we look at this, it is still nitrogen, right? And we definitely know, as we talked about last time, that you can't really change the protons, because if you change the protons, then it will no longer be nitrogen. So it's got to have 7. So it's got to be stuck there with 7 protons. In this case, if we look at the neutrons, it is still 13 minus 7, which is still going to give us 6 in this case. So it really is the electrons that change when something gains a charge. And in this case, the number of electrons would be how many? Electrons do we need? We do need 10 electrons, right? So 10 negative things plus 5 positive things, or 7 positive things there from the protons, leaves us a -3 left over, and that is basically where the charge comes from. And in this particular case, that is typically what happens when somebody becomes an anion, is they basically gain electrons. They have more negatively charged electrons than they do positively charged protons. So overall, they are net negatively charged. And that's really what the charge tells us here. It tells us, first off, it's negative, which means it gained electrons from the neutral guy. Neutral guy had 7, negative guy there had 10, so it gained electrons. The 3 tells you basically how many electrons it gained from the normal neutral guy. 7 plus 3 is 10. And that is basically what an anion is. It is somebody that will gain electrons and become negatively charged because of that. Any questions on that there? Now, if I had, we'll do the iron there, which was iron 56. So once again, with no charge, like we saw in the previous example there, our iron had 26 protons. And again, it had an equal number of negatively charged electrons, which gave us no charge. Once again, the number of neutrons was our 56 minus 26, which was 30. Now, if we took our iron here and make it a +2 charge, which is a very common charge for iron, and if we run through the same thing, again, the same logic tells us we cannot change the protons. Otherwise, once again, it will not be iron anymore. So it is locked into those 26 protons. Once again, if we subtract mass number from atomic number in this example here, it will end up with the same number of neutrons, which is 30. So once again, it is the electrons that determine really the charge. In this case, the number of electrons would be 24 electrons. In this case, we have 26 positive guys, 24 negative guys. That leaves us a net of +2 left over, which once again is where the charge comes from. And when we look at a charge like this, again, kind of like the negative charge, it does tell us pretty much what happened. The positive tells us that it lost electrons. Again, it lost electrons, so it now has more positively charged protons than negatively charged electrons, so it's net positive overall. And once again, the charge, the number, is how many electrons it lost. In this case, 26 it started with, lost 2, ends up at 24. And that is how cations happen, is they typically will lose electrons. So if you do come across something here that has charges, once again, it is only the electrons that change, never the protons, because you will change what it is. And if it's still the same mass number that you had previously, you would still have the same number of neutrons as well. Any questions on those guys there? Okay, so why don't you try one? Let's do calcium 2040 plus 2, and let's do oxygen. All right, so numbers of protons, electrons, and neutrons in each of these cases. Okay, let's take a look. So we'll start over here. So number of protons here would be our atomic number, which would be 20. Number of neutrons would be our mass minus our atomic number, which would be 20 in this case as well. And once again, as we've talked about here, it is the electrons that should change. In this case, it is positively charged, which means we have lost electrons. And how many did we lose? We lost 2 electrons. And if you're not sure, in a neutral situation, right, we should have the same number of protons as electrons there. So basically, we should end up with 18 electrons in this case, giving us the +2 overall charge. Any questions on that one there? Coming over here, our number of protons would be 8, which is our atomic number. Our neutrons here would be 16 minus 8. It's also 8. Look, I picked all the same numbers. That's good. And in this case, our number of electrons, which is what should change. Once again here, the negative means in this case, we actually gained electrons. And the 2 is how many we gained. And once again, the atomic number in a neutral situation will tell you protons and electrons. So we just add 8 and 2, gives us 10. And that gives us our -2 that's left over. Any questions on how to figure out protons, electrons, neutrons for things with charges? Typically speaking, cations, as we'll talk about in some later chapters as well, which are positively charged guys, these are typically metals, are really the guys that do that. Anions, which are again our negatively charged guys, these are really non-metals that really do that. And that's why, as we'll talk about in a later chapter, that is the basis of an ionic compound, which is basically a metal and a non-metal when they come together. When a metal and non-metal come together, they basically cause that effect in each other. Basically, the metal will give away its electrons. The non-metal will pick up the electrons. And once again, it's that positive negative attraction that we talked about the other day that is really, really strong, that holds that together. Absolutely no sharing of electrons. Also, a reminder that if you take anything from the periodic table that is not combined with anything else, it has no charge. So if you just take like iron by itself, iron metal, it has no charge. Things really only get charges when they sort of hook up, like a metal and a non-metal is really the only situation when they actually do gain charges. Any questions on any of that there? So we're just gonna finish up this chapter here, talking a little bit about energy, our big energy talk of the semester here. Energy is sort of the ability to do work or produce heat. We talked a little bit about energy earlier on in this chapter in terms of just understanding exothermic, which again releases energy. Usually, as we talked about, energy values are negative when they're an exothermic type situation, or the other sort of situation is our endothermic, which is when energy is absorbed. And usually those values are positive. When we have sort of a transfer of energy or heat, it always goes from the warmer object to the colder object. So the warmer object sort of gets colder, cooler object warms up, and if they are in sort of a insulated type container, they will meet somewhere in the middle of their temperatures and stuff like that. As we also talked about there, the law of conservation of energy, we do not create energy or destroy energy, but it definitely can be transformed from one form to the next. So a lot of times when we think about processes involving energy, we think of them as sort of a perfect transfer in a sense. Usually we deal with two things, which is the system which is pretty much anything you're dealing with. So in the case of the laboratory, like your beaker or test tube, whatever you may be doing the experiment in. And then we deal with the surroundings, which is pretty much everything outside of that. So, you know, if the system should lose a certain amount of energy, the surroundings should gain the exact same amount of energy, and vice versa. If the surroundings should lose a certain amount of energy, the system should gain the same amount of energy. It's just in terms of numbers, it's just oppositely charged in terms of the direction, exothermic or endothermic in that case. A very simple example is obviously if you light a Bunsen burner like we will do today, that is the system giving off energy to the surroundings. So obviously, if you put your hand, don't put your hand on the fire, but if you put your hand near the fire, you could feel the heat and energy coming off into the surroundings in that process. Obviously, that reaction where we light the Bunsen burner and it burning is a exothermic process in terms of the surroundings, as we can feel the heat coming in, right? It is endothermic for the surroundings as it's picking up all that heat and energy. There are different types of energy. There's radiant energy. There's thermal energy. Thermal energy is associated with the amount of atoms or molecules that you have. And the more atoms and molecules that you have in a substance, the greater the amount of thermal energy you have, the more motion that you have sort of happening with it. And that's, for example, there is a difference in terms of temperature and thermal energy. Sometimes people think they're sort of related. So for example, if you had like a coffee cup that was, you know, a really high temperature, say 90 degrees or something like that, and you had like a bathtub full of water that was at 40 degrees, it's actually the bathtub that has more thermal energy than the little cup of coffee, because in the bathtub there's a lot more water molecules and things moving around than there would be in the coffee cup, even though in the coffee cup it has a higher temperature. And that's because everybody's in a very small confined space is going to sort of give off a greater temperature than in a larger area. But in terms of thermal energy, the guy that would have the larger amount of molecules would have more energy. Chemical energy, there's energy stored in bonds. So when we actually make bonds, it's an exothermic process. So if you think about two things coming together, they're kind of wiggling around. They need to lose energy to kind of slow down and allow them to sort of come together and bond. And actually, when we make a bond, it's endothermic. We have to put energy in there to break the bond. So we have a bond together. When you put energy in, everybody gains energy. They're able to wiggle away from each other. And it's sort of an endothermic and exothermic process. So in all reactions, which basically involve all chemical reactions, which basically involve pretty much nothing but that, where you break all the bonds on the reactant side, make all the bonds on the product side, there is a net overall difference in energy that occurs from the reactant side to the product side just by that process of making and breaking bonds, which can make a reaction either be exothermic overall or endothermic overall, depending on the difference that occurs there. Nuclear energy is the energy stored within neutrons and protons. So we touched a little bit about the idea that nuclear reactions do really change elements from one to the next. And it involves really protons changing to neutrons, neutrons changing to protons. The result of those things absorb it or take a lot of energy to do, since it's within the nucleus. And it usually involves different types of radioactive particles coming out as a process of that, which is why we get sort of radiation that occurs in nuclear reactions. Potential energy is the energy due to its position. Is that classic example, the big giant boulder up there on top of the hill that's about ready to fall, right? It's got a certain amount of stored energy. It also could be pushed over the hill and start rolling down the hill, which would convert it into commonly kinetic energy, right? And as it's rolling down the hill, it will splat down on the bottom. Hopefully nobody's standing there, right? But when it hits down at the bottom, it will end up with less potential energy than it started with. But all the energy that it lost would then be transferred to like the ground, or somebody that it just crushed, right? Underneath it would get all that energy. So again, there's this perfect sort of change of energy that occurs. So as I mentioned, kinetic energy, you could calculate. We're not going to really ever calculate it, but that's how you would do there, half the mass times the velocity squared. This relationship, though, is an important relationship in terms of units for energy. We will come across some in later chapters. Again, they kind of expect you to do the energy chapter in this class, but we don't do it. But common units for energy are joules or kilojoules. Those are two very common units of energy. There's also calories, or kilocalories are also two very common ones. This is a lowercase calorie. A capital calorie is a nutritional calorie, like on the back of your food and all that. And that's actually equal to 1,000 of the little calories, which is basically 1 kilocalorie. So that's a nutritional calorie. There is a relationship between little calories and joules. It is 4.184 joules is a little calorie. But what we will see actually in the next chapter here, we will see this relationship here. 1 joule is equal to a kilogram times meters squared divided by seconds squared. So this sort of relationship that these two guys are kind of equal to each other is one that we actually do see in some calculations that we do definitely in this class. So just keep that in mind. Any questions on that there? For which one now? I'm sorry. Yeah, so 1 joule is the energy. Yeah, so basically this is 1 kilogram, right? And moving it basically meters per second at that speed to move it. It's kind of like this. You'll use this one next semester, usually in this class, but when we use something was referred to as sort of specific heat capacity. And specific heat capacity has joules per gram per degree Celsius. So this is one that's commonly used in chemistry. It's the amount of energy needed basically to raise 1 gram of a substance by 1 degree Celsius. For example, that 4.184 is the specific heat capacity of liquid water. So it takes 4.184 joules to raise 1 gram of it by 1 degree Celsius. And, something like a metal could be something like 0.4 or 0.2 joules per gram per degree Celsius. So the higher specific heat capacity, which water has a very high specific heat capacity, means that you have to put a lot more energy in there to raise the temperature of 1 gram of it by 1 degree Celsius. That is why people get upset when the ocean moves, right, the temperature just like a half a degree or something like that. It takes an enormous amount of energy just to make that water go up by that very small amount. Sometimes people think, it's just like a small little change that occurs in the temperature, but to get water to move just that small amount takes a lot of energy to do that stuff. Other questions? So I sort of jumped the gun there on the units. Whoops, come back. There we go. But again, these are some very common sort of units of energy. For us, like I said, we will see that kilogram, meter squared, second squared relationship with a joule. But other than that, we won't get too much into these other units, but we will see joules and kilojoules sort of pop up a lot. And that is also the definition of a calorie. A calorie is barely the energy needed to raise 1 gram of water by 1 degree Celsius as well. Any questions on any of that there? That wraps up chapter 1, I think. So give me a second and we will roll into chapter 2. Okay, so we're going to roll into chapter 2 here. So really in this chapter, we're going to talk about really electrons. So we're going to talk about electrons mainly. That's sort of the focus of this chapter. We're going to talk about electrons, electron configuration. We're going to talk about quantum numbers, which is sort of the basis of electrons and where they are in the atom. We'll also get into, I think, the periodic table as well along the way. And we're going to talk about waves and frequency and all that kind of stuff. So that is fireworks, appropriate for 4th of July coming up soon. But why do we see these sort of colors? The basis of a lot of what we're going to be talking about here in this chapter is the idea of electrons. And really, we do have electrons that find themselves on different energy levels. So for example, if this is, say, a lower energy level, we had an electron. At some point along the way, you could do something to it that will essentially excite the electron. It will basically excite it. It will gain energy. What happens when an electron gains energy is, frankly, it's got to move up to a sort of higher energy level. And when it does that, it really doesn't want to be at higher energy levels. So one important sort of idea in chemistry is pretty much everybody wants to do whatever they can to find themselves in the lowest state of energy. And that is sort of the most stable situation for things. And that's really the basis for what happens in chemical reactions. It sort of lowers the overall sort of energy a lot of times when things make bonds and all those type of things. So things in very high energy situations are usually very, very unstable. They don't want to be there. They want to get themselves down to a lower state of energy. So this electron, which basically gained all this energy, will eventually work its way back down, may work its way back down to the same energy level. Maybe it doesn't go all the way down there, but it will find itself trying to transfer down. Now, as we talked about, there's a sort of that conservation of energy, which means the energy to allow the electron to go up is an endothermic process, right? It has to gain all that energy to come up in terms of its energy levels. As it transfers back down, it's actually an exothermic process for the atom. It's got to release all that energy to allow the electron to come back down from a higher energy level to a lower energy level. That energy has to go somewhere, and it typically will come out in the form of a wave, and sometimes referred to as a photon of light. And this wave that comes off will have a specific wavelength. It'll have a specific energy associated with it. And for example, it could come off with a wavelength in what is referred to as the visible part of the spectrum. The visible part of the spectrum is where we see colors, like Roy G. Biv, right? Red, orange, yellow, blue, indigo, violet. And that is what happens basically with fireworks. When they launch fireworks, they basically explode them, right? Which gives a lot of energy. So all the elements that are within the fireworks, all the electrons gain energy. They go up to these higher energy levels. They then relax back down. As they're relaxing back down, they give off that energy in the form of a photons of light, which corresponds to blue or maybe green or red when we see all the colors. It's filled with a lot of atoms of those elements, right? Which is why it's, pretty good in terms of the darkness of the color that you see, right? It's not very faint or anything like that, because obviously if you shot something up that had a specific element in it, you don't have just one single atom of that element, right? You have a lot of atoms of that element, which all those guys have electrons and they're all transferring at the same time. And that gives you your sort of colors that you see. Any questions on that there? Very similar to what we're going to do today in lab. You're going to stick on a wire basically some atoms of elements, put it into a fire. That's going to excite all their electrons, and you will see colors that will come out in flame basically as these electrons transfer. If you ever, for example, boiled water for making pasta, maybe you put salt into your water and it may be overboiled at some point, right? And it's the flame changes color, right? If you're using a sort of a gas flame underneath there, and that's basically the sodium coming out of your water and those sodium ions being excited, and that's why it turns kind of like an orangey yellowish type flame when it hits and stuff like that. It's basically those electrons being excited in that. Go home and try it. No, don't make a mess at home. So again, that's why we we do see colors is really these electrons transferring. Now, does all the electrons transferring result in waves that really hit the sort of visible part of the spectrum? The answer is no. They could come off in other parts of the spectrum, maybe where you might feel heat or something like that. But definitely the ones that obviously come off in that range of that visible part where we can see colors does give us those colors. All right. So one way that sort of energy is transferred through space is through what is referred to as electromagnetic radiation, and really transferred through waves. And waves have some different characteristics. We could have a wave that looks something like this. And a wave, one of the main sort of characteristics of it is lambda, which is the wavelength. And it's basically the distance between two sort of peaks or troughs in a wave. The frequency is usually abbreviated with, people call it a V, but it's a nu. And that is really how many times a wave passes a point within a second, for example. Typical units, by the way, of wavelength are meters, are nanometers. But a lot of times it is meters that we use a lot in calculations, or you need to convert things to meters in calculations. But sometimes the final answer is reported in nanometers, but mainly meters is the main one there. The frequency in terms of units is typically reciprocal seconds, so 1/seconds. And by the way, a reciprocal second is the same as a hertz. So that's also a very common unit of frequency is a hertz. The speed of the wave, again, is, a lot of times given in something like meters per second. So how fast it's moving, obviously how long it's moving in meters per second. There is, as we will talk about, a relationship between basically the wavelength and the energy. And as we will see, things with very long wavelengths are usually very low in energy. Things with much smaller wavelengths are usually very high in energy. Things with really small wavelengths have typically a lot faster or higher frequency because they occur a lot quicker. And things with a longer wavelength takes a little lower frequency because it takes longer for it to sort of move through space as it's kind of winding through it, as opposed to something that's kind of moving really quick with a very short wavelength. Any questions on that there? So here's our characteristics, which apparently the boxes got lost. So again, that is lambda in there. That is the nu. And as I mentioned, is that distance between them. And here's an equation that's an important one that you need to know. And that is c, which is the speed of light. Personally, some people like to use this. I think even in your lab manual, they use the big number. Personally, I go with 3 times 10 to the 8 meters per second. So you can use either number, but I personally round to 3 times 10 to the 8. So that's the speed of light is equal to the wavelength times the frequency. And again, since c is meters per second, that means when you use this equation, the wavelength needs to be in meters. The frequency should be 1/seconds, which will once again give you meters per second when you do it. So those are typically the ones we need it. If we need to rearrange this and solve for the wavelength would equal the speed of light divided by the frequency. And if we want to solve for the frequency would be the speed of light divided by the wavelength. So as we talked about yesterday as well, you want to make sure, obviously, use your exponent button. Yes, definitely in this chapter. Don't use anything other than your exponent button when you're punching those numbers in. So those are sort of the couple of rearrangements. So basically, if you know the frequency, you can figure out the wavelength, and vice versa. Obviously, if you know the wavelength, you can figure out the frequency of that wave that goes through there. So why don't we try one here, calculate the wavelength of red light with a frequency of 4.62 times 10 to the 14 reciprocal seconds. Why don't we do it in both meters and nanometers? So why don't you calculate both of that? Nano is 10 to the -9. Okay, let's take a look. So here we are going to try to find the wavelength. So obviously our C is equal to our wavelength times our frequency. Our lambda there is our wavelength. So we will solve lambda will be, we're going to divide this guy to the other side. So it's going to be C divided by our frequency in this case. C again is a constant. So you always have it as 3 times 10 to the 8. So putting our numbers in here gives us 3 times 10 to the 8 meters per second divided by our frequency, which was 4.62 times 10 to the 14 reciprocal seconds. We want to make sure we use our exponent button here. And if we do 3 exponent 8 divided by 4.62 exponent 14, there we go, gives us 6.49 times 10 to the -7. The units here are meters, as these guys will cancel. First off, any questions on that one there? At this point, we want to go nanometers as well. So nano is 10 to the minus 9. A reminder that that means in 1 nanometer, there are 10 to the minus 9 meters. Again, not reversed around. Taking our number there in meters and converting it. In this case, we would want the 10 to the minus 9 on the bottom is 1 nanometer. The meters will cancel. So we're basically taking this and dividing it by 1 times 10 to the minus 9, and that's going to give us 649 nanometers. Any questions on either of those calculations? Reason we did nanometers on this one as well is because this is red light, which is in the visible part of the spectrum, and typically the visible part of the spectrum, as we'll see in just a sec here, is typically given nanometers a lot. So everybody else outside of that is usually given in meters, but any type of visible part where it's a color is a lot of times given in nanometers. Any questions? All right. So why don't you try this one here? Calculate the wavelength of the red light. Is that the one we just did? That is right. We just did that one. Hang on here. Let's not do that one again. Let's do this one here. There we go. Calculate the wavelength of a radio signal that has the frequency of 100.7 megahertz. Mega is 10 to the 6. Look, so in this case, we're given the frequency, which is 100.7 megahertz, and we are looking for the wavelength there. So we will use our equation, our speed of light is equal to our wavelength times our frequency. In this case, solving for wavelength would give us C over frequency. In this particular case, we do need to do a little bit of work here in terms of units. This is megahertz. Remember, though, that a hertz is equal to a reciprocal second. So we really got to get rid of the meg part of it. Otherwise, we're going to be off because the speed of light is in meters per second. So we do need to get it into sort of seconds rather than obviously megaseconds, if you will. So we do want to do that sort of conversion first there to take it from 100.7 megahertz. And once again, the 10 to the 6 means that in 1 megahertz, there is 10 to the 6 hertz. So that is what we would want to use it like. So if we do that, in this case, we're going to take 1 megahertz there is going to give us 10 to the 6 hertz. And that would get us 100.7 times 10, 1 times 10 to the 6. And that gives us something like 1.007 times 10 to the 8 hertz, which is the same thing as 1.007 times 10 to the 8 reciprocal seconds, as they are equal to each other. Any questions on that there? At this point, we could then go into our wavelength is our 3.0 times 10 to the 8 meters per second divided by our 1.007 times 10 to the 8 reciprocal seconds. Now we are good. Those seconds are going to cancel out and we will be left with meters. Otherwise, once again, we'll be off by a factor there. So 3 to the 8 divided by our answer there is like 2.98 meters. Any questions on that there? 2.98 meters is much larger of a wavelength than our previous guy, which was 6.49 times 10 to the minus 7. That right there should tell you that radio waves is a lot less energy than visible part of the spectrum there where we see light, which is why we can listen to our radio and not be in so much problems of energy belting us down. Any questions on how to calculate these things? Biggest problem for people is units. Yeah, so you just got to watch the units, make sure everything will cancel out correctly. Okay. All right, so as I mentioned before, whoops, come back. There we go. As I mentioned before, the wavelength is sort of related to the energy of a wave. And as we can see here, we even see some differences, obviously, with different colors, because they do come off at different parts of or different wavelengths. We can see red here has a much larger wavelength than, say, green, and green has a larger wavelength than blue. So again, sort of the relationship, as we will see in terms of energy and our waves, is the longer the wavelength, the sort of lower the frequency and the lower the energy that you see. And the shorter the wavelength, the higher the frequency and the higher the energy that you see associated with it. So if we look at these three colors here, we definitely would say that red would be the lowest in energy of these guys, because again, it has the longer wavelength, while blue here would have the highest energy, as it has a much shorter wavelength. As you can see there, just a higher frequency happening, and has a lot more energy associated with it. And we see that by our sort of hertz. This guy has 4 cycles per second. This guy has 8. This guy has 16. So it's obviously moving a lot more faster, if you will, a lot more repetition of that wave happening. So when we talk about sort of electrons, as we've been talking about, sort of transitioning from one wavelength to the next, again, depending on sort of the wavelength of light that comes off, it may correspond to a specific part of what is referred to as the electromagnetic spectrum here, which is what we're looking at. And on this spectrum here, we have on this side really a much longer wavelength. On this side, a much shorter wavelength. So what that means in terms of energy is on the right-hand side of this particular picture here, this would be the lower in energy side. Over here would be the higher in energy side. And we have different parts. So sort of on the longer one, like the calculation we just did, we have what are referred to as radio waves, like we listened to there in our car. With red, so you can see it. Again, a little bit longer in wavelength, lower in energy, not too bad. As we move next, we have microwaves. Has a little bit more energy associated with it, enough energy to make your water molecules in your food move really, really fast and heat it up. And then we get our pizza in like 3 minutes and all that good stuff, As we go a little bit more to the left here, a little shorter of a wavelength, we get the infrared part of the spectrum. So if a wave comes off, as we talked about earlier, again, it won't always come off in the visible part of the spectrum. Maybe it comes off here in the infrared part of the spectrum. And that is, again, where we sort of experience heat and that type of feeling. A lot of what we deal with, and obviously what we will be dealing with today when we do flame tests, is the visible part of the spectrum. That is the part of the spectrum where we actually can see color occur. And that is our Roy G. Biv, right? It's our red, orange, yellow, green, blue, indigo, violet sort of happening there, right, as we go across there. And even in colors here, we have, as we just talked about, differences of energy. The red color is lower in energy than more the violet color over here on this side of the spectrum. And past that, we do have ultraviolet. That's the UV part. That is a lot shorter of a wavelength, more energy. That is why we have to put sunblock on right when we go outside, so we don't get too toasty as we're sitting in the sun. X-rays, that is why they put a lead vest on you when they take an X-ray, right? And they walk out of the room, so they shoot you with X-rays. It's usually very high in energy. And gamma rays, as we talked a little bit about the other day or yesterday when we were talking about sort of the different type of radioactive particles, those are pretty much just pure energy. If you ever work with anything that is a gamma ray emitter, you need a lot of sort of protection to make sure that you're sort of safe if you're using that, like lead, concrete, and those type of protections and stuff like that. So energy increases on this picture as you go to the left. and also the colors as well. As I mentioned before, the visible part of the spectrum is usually given in nanometers. Pretty much everybody else on the spectrum is usually given in units of meters along the way. You are responsible to know these guys. You are responsible to know them, sort of the order. You don't have to know any specific numbers of like where they break off or anything like that, but you need to be able to put these guys in order. For example, of a question like, put them in order from lowest energy to highest, X-rays, UV and all those kind of things are longest wavelengths to shortest wavelengths. So that's what you need to know. You don't, again, need to know any of the specific numbers or anything like that, but you do need to be able to kind of put them in order based on energy, wavelength, and that type of stuff, frequency. That includes the colors as well. You need to know sort of the order that red is lower in energy than, say, the violet side and all that kind of stuff. Any questions on any of that? Okay. So let's talk about energy, and as these electrons transfer from one level to the next, energy is really gained or lost in really multiples of, I'm not sure what it is, but I think it should be E there, of E. And when we talk about electrons transitioning, we talk about electrons sort of transitioning, either gaining or losing energy in what is sometimes referred to as a quanta of energy or a packet of energy. Basically what that means is sort of a simple explanation of that is, we have these different sort of energy levels. And if you have an electron, it will either gain enough energy to find itself to, say, this energy level, or it'll gain enough energy to find itself to that energy level. It will never gain energy where it kind of finds itself, kind of in the middle of two energy levels, just kind of hanging out and stuff like that. We'll see a picture a little later, but you could think of it sort of like stairs, right? When you go upstairs, for example, you typically have enough energy to get to this step, to this step, to this step. You don't usually go halfway between steps and go, I'm just going to take a rest right here and see how that goes, right? Because you're going to fall. Just like when people go upstairs, some people could just do one stair at a time. Maybe there's somebody that could, jump 2 stairs at a time or something like that, or go up 2 stairs at a time. So, electrons travel that way. Some have enough energy, maybe just to pop up to the next one. Some have enough energy to get up to a few more energy levels along the way. So that is the idea of quantized energy. Electromagnetic radiation is a stream of particles, which are referred to as photons. So energy is absorbed that way and sort of given off that way in the form of light, which is sometimes referred to as photons. There is an equation here, and it is missing the middle part there, and that should be H times the frequency. H is what is referred to as Planck's constant, and it is 6.63 times 10 to the minus 34 joules times seconds. The frequency obviously is the same frequency in reciprocal seconds, or hertz. So when you look at units here, E is equal to H times the frequency. H is joules times seconds. Frequency is 1 over seconds, so the seconds cancel. So when you use this equation, you end up in units of joules at this point, which again is a unit of energy. And because using our earlier equation, C is equal to the wavelength times the frequency, if we solve for frequency, it is C divided by the wavelength. You could also say that the energy is equal to HC divided by the wavelength. So that is where this part comes from. Which gives you a nice situation where if you frankly only know the wavelength, that's all you need. You can figure out the energy from that. And once you have the energy, you can actually figure out the frequency as well. Or if you know the frequency, you can figure out the energy associated with that wave. So if you know the frequency, you can just times it by Planck's constant, and you'll get the energy associated with that wave or photon of light. Or if you know just the wavelength, you could times it by H and C, which are both constants, and both values will be given to you, obviously. and you could just use it as well. The other thing that you do want to be sure of as well, once again, is that the wavelength here is in meters, so that it will cancel out correctly with the speed of light, which once again is also in meters per second. Any questions on that there? So Einstein sort of saw, that's Einstein's equation there, E is equal to mc squared, mass times the speed of light squared. That, basically there's this idea of sort of the dual nature of light. So particles do behave like waves in certain aspects. So they do have wave-like characteristics, and waves also sort of behave like particles as well. So when we talk about specifically the particles in this sort of chapter, which is really electrons, do have sort of a wave-like component and also behave like particles as well. And it's that sort of dual nature. So you could sort of apply sort of wave-like function to things like electrons as they're moving around and stuff like that, as addition to particles. So when electrons transfer from one energy level to the next and sort of go down in energy or even go up in energy, we do get some different types of spectrums. When an electron goes up in energy, it is absorbing energy, and it is, as we talked about, endothermic, and that is sometimes what is referred to as an absorption spectrum. When an electron is already in a higher energy level and sort of is relaxing back down, that obviously is releasing energy, and that is exothermic, as we talked about. And that is usually what is referred to as an emission spectrum. For us in this class and most things that we see, it will be really the emission spectrum that we're looking at as they're coming back down in energy and releasing that energy, and again, giving off that. They could do it in two different ways. Thing like the sun, for example, and sort of like when you heat metals and stuff like that, they sometimes will give off what is referred to as a continuous spectrum, and that's when white light is passed through a prism. It basically contains all the wavelengths of visible light, so like everything's coming off at once. It is definitely not quantized energy that's happening there. It is a continuous energy, and that's different than how elements sort of give off energy. Elements give off what are referred to as a line spectrum, and each line corresponds to really a distinct transition of an electron from one energy level to the next. And this is sort of like what I just drew a second ago. A continuous spectrum, you could kind of think of like if you were walking up, right? If you were walking up a ramp, you pretty much can walk anywhere at any point, right? And you could be anywhere along the way. What happens in a continuous spectrum, you get everybody coming off at once, you could be anywhere at the same time. In a line spectrum, again, it's more quantized energy, where you got sort of the staircase thing where you got to either be at this energy level, or that energy level. And because there's only specific transitions that occur, it results in specific waves coming off pretty much all the time in the same spot. Because, hey, that electron went from the fourth to the first energy level, and it will do it again. So we end up getting line spectrums, which pretty much like the name sounds, you get these distinct lines that occur when you look at it through like a spectroscope, which I think is tomorrow's experiment. We're going to look at this here. And you look at it through a prism, it would be separated out, and you'll see these distinct lines as specific, for example, colors, which correspond to specific wavelengths of light. And each of those colors that you see is responsible for, say, an electron that was, say, on the fourth energy level that went all the way down, say, to the first energy level, is going to give off a specific wavelength, as opposed to if you had an electron on the third energy level that only transferred down to this second energy level. Which one would be the longer, which one would be the more energy associated with it? The one going from 4 to 1 or the one going from 3 to 2? Yeah, the first one, right? It's got to go from the fourth to the third to the second, then all the way down to the first, right? A lot more energy associated with that transition than just going from like one level to the next and the second one. Because this guy would have more energy, right? Then say that guy, which one should have this shorter wavelength? The first one here should also have the shorter wavelength, right? Which would respond to a color perhaps maybe like towards the violet side or blue side of the visible part of the spectrum if it came off there. While the guy on the right there only transitioned a small amount of energy, which would have a longer wavelength, and perhaps it would correspond to, like, if we were talking about the visible part of the spectrum or the red side of that colors type of thing. So depending on sort of how far they are traveling will correspond to obviously the different lines that you see, and that obviously corresponds to perhaps to why you see different colors, because one is obviously a longer transition than another one as it's moving. Any questions on that? So hydrogen's emission spectrum allows for really only certain energies of the electrons in the hydrogen atom, and it definitely is quantized. And this idea of Bohr and his model hydrogen atom, really electrons are in fixed orbits. It can only travel from one energy level to the next. All right. So obviously the significance of, hydrogen emitting these specific ones is it tells us really that the energy there is quantized, is moving from one specific energy level to the next. And otherwise, if it was sort of white light, we would have more of a continuous spectrum where we sort of see everything that happens there. And that brings us to Bohr model of the atom. And Bohr, had what is sometimes referred to as sort of a planetary model of the atom. And that is where we have the nucleus sort of in the middle. And we have these different orbits, if you will. As I run out of room on that side, we'll just go that way. And these different orbits are where electrons are moving around the nucleus, again, in this sort of circular pattern, this planetary pattern, which, as we sort of touched upon, we'll touch upon a little bit later on in this chapter, not really correct. They don't really move that way, but this was sort of the idea. And Bohr's model meant that, this electron is either in this first energy level, which is n equals 1, maybe it's in the second energy level, which is n equals 2 or n equals 3. And by the way, is what is referred to as the principal quantum number. And that is a really fancy way of saying that's the energy level. And it basically can go from n could have values of 1 through 7. A value of n is equal to 1 is the lowest energy state you could have, is sometimes referred to, as it says here, the ground state. So that is the lowest energy. That is sort of the one that is closest to the nucleus. Anything that's above that, anything that is like n is equal to 2 through 7, those are what are referred to as excited states. And those are basically higher in energy. So the idea of sort of Bohr's model of the atom here, hydrogen atom, is what we see in terms of the sort of 4 major colors in the line spectrum of hydrogen is, again, an electron may be working its way back down from the third energy level to the first. Maybe it's going from like the second to the first and so forth. And again, as it is doing those sort of quantized transitions, it will be obviously releasing that energy in the form of light, which again, those correspond to the different sort of colors that we see in hydrogen, which I think we might have a picture. Here we go. So once again, here we have these transitions that are occurring, and we have some colors that we typically see. Obviously, this first transition here, which give us the red sort of line that we would see in the spectrum. And again, you can see it's really just a transition between, say, the third energy level to the second. Not a lot of difference in energy happening there, which again would correspond to a longer wavelength, which red is longer than the transition we see here for what we would see, say, for the blue line that would occur for hydrogen is that electron transitioning down from the 5th energy level or whatever it may be there, down to the 2nd energy level. So a lot more energy difference is occurring there, resulting in a much shorter wavelength, and then that represents more of a blue type color that we see. Obviously green sort of in the middle there of those two. So those electric transitions that occur between electrons, again, sort of restricted to being in one of these sort of orbits. Again, we would never find an electron just kind of stopping in between the different orbits. Again, with that quantized energy, it will make itself to one or some other orbit there, never stopping in between along the way. And that's again why hydrogen and other atoms sort of give off these really distinct sort of line spectrums. The line spectrums are so distinct that every element has its own line spectrum. So you can identify a particular element by the actual colors that you see, and actually the wavelengths where they come out at are different for every element. So every element will have a different line spectrum, and that is sort of what we'll do tomorrow. You'll kind of look at some and then have an unknown and go, okay, I see lines at this, I think it's, you know, this element or whatever it may be. So every element will have that same thing. We could also calculate the energy associated with the transition of an electron from really one energy level to the next, and we could use this equation here. That delta E is the change in energy as an electron goes from one energy level to the next. It is equal to minus 2.178. Again, personally, I go with minus 2.18 is actually the number there. Times 10 to the minus 18. So if you want to do a little rounding, you can. This is also what is sometimes referred to as Rydberg's constant. So that is what is known as Rydberg's constant, 2.18 times 10 to the minus 18 times 1 over n squared final. That is the final energy level of the electron where it ended up, minus 1 over n squared initial. That is the initial energy level where the electron started. This is also the same energy that is Planck's constant times the frequency, also hc over the wavelength. Yeah, so basically you could use this. You calculate the energy of that transition of that electrons from one energy level to the next. You could actually use all the other ones to figure out the wavelength associated with it and the frequency associated with it by sort of substituting those guys into there. So they all kind of tie together, you know, these sort of equations. Any questions on that there? Once again, as we talked about, we would expect, obviously, if an electron was going from a lower energy level to a higher energy level, we would expect the E to be positive or endothermic, right? If it's gaining energy. We would expect that the delta E would be negative if the electron started at a higher energy level and coming down to a lower energy level. Now, in relationship to sort of tying these guys into these other equations that we saw before, there's really an important thing that we do when we do these type of calculations, and that is when you calculate the energy, you should keep the positive or negative depending on whatever type of number that you get. And that's important to tell somebody that in this process it's negative, so we're releasing energy, or it's a positive number for energy, we're gaining energy. You should get rid of the negative sign if you have one when you go then put it into these equations here and calculate something like the wavelength or the frequency. Those values should always be positive. Okay, so there's sort of a little calculation thing that we do here. And again, tomorrow as well, you know, you will calculate energy. You will a lot of times get a negative value for energy. And sometimes people leave the negative and then put it into the wavelength sort of equation or the frequency equation, end up with a negative wavelength or frequency, and you should not end up with a negative wavelength or frequency. So you just drop the negative for that part of the calculation, but you absolutely should leave the positive or negative for the energy value, whichever one that you get. That makes sense? Yeah. Any questions on that there? Okay. So in terms of Bohr's model of the atom, and it is a model, sort of like a theory, it works really well for the lines that we see for hydrogen and that sort of quantized energy. It does sort of fall apart when you get into elements that actually have more than one electron, so that's not so great, but it does really nicely explain what we do see there in the hydrogen. And as we'll talk about a little bit later on in this chapter, that's why we sort of move away from Bohr's model, that sort of planetary model of those electrons moving in pretty circles, sort of around the nucleus, to more of a quantum mechanical model where, we don't really know how they're moving about the nucleus and stuff like that. So as an electron becomes more tightly bound, its energy is more negative relative to the free one, and it's sort of brought closer to the nucleus. So again, that accounts for, that opposites attraction between those electrons, and they're sort of bound to the nucleus. So, we sort of move away from this model, but that idea of the dual nature of light for particles, they could have wave-like functions, much like a wave, even though it's sort of randomly moving, it is sort of tied to the nucleus by that attractive force, and that's why it sort of has sort of wave-like functions, because it can't just kind of freely sort of move around, and it sort of moves around more like a wave in that sort of characteristic. So Bohr's model is incorrect. Again, it really only works for hydrogens, and again, the take-home message once again is they do not move around in these pretty circular orbits. We move away from the idea of orbits to, maybe you're familiar with, and we'll talk more about next time, these idea of orbitals like S, P, D, and F orbitals as sort of theoretical ideas of where electrons are found within the atom and stuff like that. Basically, electron configuration is sort of the idea there behind that. All right, so this is way too long of an example, so we will stop here and we will open up with this calculation tomorrow, which is good because that'll be very similar to what we will be doing tomorrow in lab. Any questions on anything we talked about here today? All right, we will lay it up there then.